Part 1. On a clear night, when you step outside and look up at the sky, you see thousands of stars shimmering in the darkness. Each one feels like a tiny, distant point of light, almost within reach. But in reality, most of those stars are unimaginably far away, separated from us by hundreds or even thousands of light years. Yet among that vast ocean of distant suns, there is one star that, at least in cosmic terms, is surprisingly close. That star is Proxima Centauri, a small and faint red dwarf located in the constellation Centaurus. At a distance of about 4.24 light-years, it holds the title of being our nearest stellar neighbor beyond the solar system. This star was discovered in 1915 by the Scottish astronomer Robert Innes. Despite being the closest star to us, it is so dim that it cannot be seen with the naked eye. Its faint reddish glow is only visible through telescopes, making it almost invisible compared to brighter stars in the night sky. Proxima Centauri is much smaller and cooler than our Sun, emitting only a fraction of the light and heat. And yet, what makes it incredibly fascinating is not its size or brightness, but its proximity. It is part of the Alpha Centauri system, which is the closest star system to Earth, making it the most logical destination if humanity ever attempts interstellar travel. At first glance, 4.24 light-years might not sound like an overwhelming distance. It almost feels like something we could eventually reach with enough technological progress. But the problem lies in what a light-year actually represents. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. That adds up to roughly 9.5 trillion kilometers in a single year. When you multiply that by 4.24, the distance to Proxima Centauri becomes approximately 40 trillion kilometers. That number is so massive that it becomes almost meaningless to our brains. To make this more understandable, imagine driving a car at a constant speed of 100 kilometers per hour without ever stopping. No brakes, no sleep, no interruptions. Even at that speed, it would take over 45 million years to reach Proxima Centauri. That's longer than human civilization has existed, longer than recorded history, longer than anything we can truly comprehend on a human timescale. Because of its relative closeness, Proxima Centauri has often been considered humanity's best chance of reaching another star. If we were ever to leave our solar system and travel to a different star system, this would be the most obvious target. But as appealing as that idea sounds, the reality is far more complex. Even this nearby star presents challenges so enormous that they push the boundaries of physics, engineering, and human endurance. To understand why this journey is so difficult, we first need to rethink how we measure distance. On Earth, we use miles or kilometers, and those units work perfectly fine for everyday life. But once we step into space, those familiar measurements quickly become inadequate. Even within our own solar system, distances are measured in millions and billions of kilometers. When we start talking about stars, those numbers grow so large that they lose any intuitive meaning. Let's take a look at the fastest spacecraft humanity has ever built. Parker Solar Probe can reach speeds exceeding 700,000 kilometers per hour when it gets close to the Sun. That's an incredible achievement, representing the peak of our current engineering capabilities. And yet, even at that extreme speed, it would still take about 6,300 years to reach Proxima Centauri. That is longer than the entire span of recorded human history. Now consider Voyager 1, which has been traveling through space since 1977 and is currently the most distant human-made object ever created. It is moving at around 61,000 kilometers per hour. At that speed, it would take more than 73,000 years to reach Proxima Centauri, and that's assuming it was even heading in the right direction, which it is not. These examples highlight a fundamental problem. On a cosmic scale, even our fastest machines are incredibly slow. The real challenge is not just distance, but the relationship between distance and speed. If we want to reach another star within a human lifetime, say within a few decades, we would need to travel at a significant fraction of the speed of light. Experts estimate that we would need speeds of at least 10 to 20% of light speed to make such a journey feasible. But reaching those speeds introduces an entirely new problem: energy. The amount of energy required to accelerate a spacecraft to even a fraction of the speed of light is enormous. The heavier the spacecraft, the more energy it needs. And here is where things become even more complicated. The fuel required to generate that energy also has mass, which means it too must be accelerated. This creates a chain reaction where more fuel requires even more fuel, leading to an exponential increase in mass. This problem is described by what scientists call the rocket equation, and it reveals the harsh limitations of traditional propulsion systems. Even with the most advanced chemical or nuclear propulsion technologies we can imagine today, the amount of fuel required quickly becomes impractical. To accelerate even a relatively small spacecraft to 10% of the speed of light would require an amount of energy comparable to the total annual energy consumption of entire countries. And that only accounts for accelerating the spacecraft. Slowing it down at its destination would require the same amount of energy all over again. So the challenge of reaching Proxima Centauri is not just about covering a large distance. It is about overcoming limits set by time, energy, and the fundamental laws of physics. What appears to be a nearby neighbor on a cosmic map turns out to be a nearly impossible destination with our current level of technology. Even if we somehow found a way to overcome the immense energy requirements, another major obstacle would immediately stand in our way: propulsion technology. Every propulsion system we have developed so far is designed for travel within our solar system. None of them are capable of handling the extreme demands of interstellar travel. Traditional rocket engines, like those used in missions to the moon and beyond, operate by expelling high-speed exhaust gases to generate thrust. This method works well for shorter distances, but it becomes highly inefficient when we try to scale it up for interstellar travel. To achieve higher speeds, rockets need exponentially more fuel. For a journey to Proxima Centauri, a spacecraft would need to carry such an enormous amount of fuel that its total mass would become unmanageable. In fact, even a spacecraft the size of a skyscraper would be made up of more than 99% fuel and still would not reach the required speeds. More advanced systems like ion engines offer better efficiency and are already used in space missions. However, they produce very low thrust. While they can operate for long durations, they accelerate very slowly and cannot achieve the extreme speeds needed for interstellar travel within a practical time frame. Nuclear propulsion has long been considered a potential solution. Concepts such as Project Orion proposed using controlled nuclear explosions to propel a spacecraft forward. In theory, Such systems could reach a few % of the speed of light. However, in practice, they introduce enormous engineering challenges, extreme structural stress, and serious ethical and political concerns. Even with such advanced concepts, the journey to Proxima Centauri would still take centuries. Beyond all of these technological challenges lies an absolute limit imposed by the laws of physics, the speed of light. According to the theory of relativity, nothing with mass can travel at or beyond the speed of light, which is approximately 300,000 kilometers per second. As an object approaches this speed, the energy required to accelerate it further increases dramatically. Eventually, it would require an infinite amount of energy to reach the speed of light, making it fundamentally impossible. But even if we imagine that all of these barriers could somehow be overcome, the journey itself would present a completely new set of challenges. A trip to Proxima Centauri would take decades at best, and more realistically centuries. During this time, a spacecraft would need life support systems capable of operating flawlessly for extremely long periods. Air, water, and food would need to be recycled continuously in a closed system, with no room for failure. Even a minor malfunction could jeopardize the entire mission. Radiation exposure is another serious